and the head of the Research Center FSCN at Mid-Sweden University. I will be your host and the chairman of this session today. We will begin by presenting all the key people here. First of all, of course, Rana Alimohammadzadeh, who is the writer, the PhD student who will defend her thesis. You see probably Rana, you can wave your hand maybe. So there is Rana. Then we have the opponent, Professor Monica Ek from KTH, the Royal Institute of Technology. I hope that, yeah, if you put on your, there is Monica. Then we have the examination committee, where we have adjunct professor Thomas Granfeldt from Miyun, and he was previously also working at Valmet AB. There is Thomas. Next, we have Dr. Rauni Seppänen, Holmen AB. There is Rauni. There is Rauni. Good. Professor Juha Fiskari from Mid-Sweden University. There is Juha. Excellent. Professor Josef Samec from Stockholm University. There is Josef. And Professor Gunnar Henriksson from KTH, the Royal Institute of Technology. There is Gunnar. He is somewhere into cyberspace, I hope.
I'm here.
There you are. I just don't see you. That's the reason. Yeah. I have a wrong mode here. Right. As you can see, it's always a little bit exciting with this Zoom meeting or using Zoom and doing everything online. We have two very able, I would say, directors or help with us, Inger Axbrink and Kristin Grafström, who will be keeping control of the video and everything. And when we get to the questions part from the audience towards the end of this session, then the way to do it is to raise your hand so that I can see the hand in Zoom, so that I can see who wants to talk. And if you have any problems, use the chat and we get help from on either Inger or Christine. I hope that I haven't missed anything important that I have to say right now. Next, the thesis that we are going to examine today, that's entitled Eco-Friendly and Catalytic Surface Engineering of Cellulose and Nanocellulose. It's by Rana Alimohammadzadeh. As I said, the thesis has been performed at the Department of Natural Sciences and the Research Center FSCN at Mid-Sweden University. The main advisor of the thesis has been Professor Armando Cordova. I don't know if we get you in the picture.
Hi.
Yes, sorry, I have a little too small screen here. So Armando has been the main supervisor, and then the co-supervisor has been Professor Dan Bylund. Dan is probably, as far as I can see, he's not here today. No.
He is here. He is
here.
Thank you, Inger. Supporting us in the room.
Okay, that's how it goes. That's why I don't see you on the list. So Dan is there. The thesis has also been done in collaboration with Professor Lars Bylund at KTH and Professor Per Engstrand at Miyun. let's see if they are present here. I don't see Lars on the participant list and not Per. And in addition to these collaborations, academic collaborations between different research groups at MIUN and KTH, collaboration with industry has been very important in Rana's PhD work with companies such as Tetra Pak, More Research, and Billerud Korsnäs, where we have got sample materials and run different experiments. The next thing, I need to ask Rana if there are any formal errors that you would like to inform us about before we begin the actual.
Yes, actually, yesterday I sent to the Professor Monica Ek and the committee by mail.
Can you just briefly say what the errors are, if they are?
I don't have it here.
Okay, well, there are some, maybe we come to that while we go through the thesis and discuss it and so forth.
Yes.
Good. Okay, what happens next is that Rana will go to, give us an overview of the thesis, the main findings and so on. Then we will take a short break, say 10 minutes or so that we can maybe fetch a cup of coffee or something. And then we'll commence with the discussion questions by Professor Monica Ek. After that comes the examination committee, and then everybody in the audience is welcome to pose questions to Rana. And once we are done with all questions, then we will have the examination committee will have a separate meeting and make a decision if the thesis can be accepted or not, and we get back after that and close the session. So with that, I will give the word to Rana. Please.
Hello, everyone. First, I wish thanks Professor Niskanen for nice introduction. Today, my topic is eco-friendly and catalytic surface engineering of cellulose and nanocellulose. The non-stop use of petroleum-based material such as plastic causes severe environmental problems, including pollution of the ocean and increasing the CO2 level, also some diseases such as cancer due to the toxic monomer. Subsequently, we need to sustainable material to overcome this issue. Cellulose, the most abundant biopolymer, which was discovered by Payen, it can be extracted from trees, shrubs, and herbs. Also, it is found in algae, bacteria, and some marine animals. The almost pure cellulose, 90%, can be extracted from the cotton. In a microfibrillated cellulose, we have both amorphous part and the crystalline part, and dependent on the treatment of the cellulose fiber, we can manufacture two kinds of cellulose, CNF and CNC. With the fibrillation of cellulosic fiber, we can produce CNF under high mechanical sharing, and with the acid hydrolysis, we can break down the amorphous part and release the crystalline part, that we will have a crystalline nanocellulose. With the mineral acid hydrolysis have been studied extensively, but with the respect to the environmental impact, hydrolysis with the dicarboxylic acid became interesting topic. This nanocellulose has a set of property that it give us the opportunity to use it in a variety of the industrial and biomedical application. But this biomaterial is highly moisture sensitive, and it needs to, it's required to be modified to be applicable in many uses. Surface modification of nanocellulose can carry out during the modification and or post-modification. Chemically treatment with the tempo oxidation, carboxymethylation, sulfoethylation, or phosphorylation normally used for decreasing the energy consumption during the CNF production. It means that after this produced CNF also will be functionalized with these chemicals. And also during the acid hydrolysis with the sulfuric acid or carboxylic acid, we will have the functionalized CNC. But today, my topic is about the post-modification. In 2005, Hafren and Cordova, they did the esterification of cellulosic fiber using organic acid to do the esterification, direct esterification, or ring opening polymerization. Having this knowledge in the group, then in my thesis, I used this organic acid, mostly L-tartaric acid and the citric acid, to modify cellulose and the nanocellulose. Paper 1 is about the hydrophobization of nacre-inspired nanocomposite with alkoxysilane in the presence of organocatalyst. Paper 2 is about the preparing superhydrophobic CNC film with the combination of self-assembly and organocatalytic modification. Paper 3 is about the direct esterification of CNC with thioglycolic acid. And in paper 4, we have a synergistic combination of organocatalyst and polyelectrolyte to improve the strength property of fiber. Natural composite design from organic and inorganic materials has gained a high academic and industrial interest. In this context, nacre-inspired nanocomposite has gained a high scientific research interest due to the exceptional stability and excellent mechanical property of nacre. But we wanted to prepare NTM CNF nanocomposite with a functional group and also hydrophobic nanocomposite. For this, we choose enzymatically derived CNF as a biomaterial and NTM as an inorganic material. It's proven that NTM is used for increasing the strength property of the composite. Also, it gives a good barrier property to nanocomposite. We aimed in the beginning of this work to prepare hydrophobic nanocomposite within the click chemistry and with the filtration system. Then I did separately modification of CNF and NTM to do the click chemistry and to prepare nanocomposite. But the idea failed because of the agglomeration of this material after modification. Then we thought about the post-modification and preparing CNF and NTM nanocomposite within filtration system, which has been studied a lot with the Professor Lars Berglund group, and drying in a rapid cotton sheet former. Then within this, we could have a nanocomposite in 80 to 20% CNF and NTM ratio. But then in the following, we did the modification of this nanocomposite with the alkoxysilane in the presence of tartaric acid, toluene in 95 degrees. Here is the catalyst screening of the modification. Here we see that comparing entry 2 and entry 4, the result, we have a high value of the contact angle when we had just the catalytic amount of L-tartaric acid. Also, we can see in entry 3 that when we had a catalytic amount of this organic acid, we could reach even higher contact angle value to compare in a without catalyst and in 48 hours. And when we did this reaction with the mercaptocylon, then we get even higher value. Also, we did this reaction with the citric acid and acetic acid, and with the citric acid, we had a higher value than compared to tartaric acid. I continued the modification with the L-tartaric acid, and here I noticed that the modification with the fluoroalkan is faster. In 6 hours, it reached to high value contact angle, but the result of the mercaptocylon is comparable with the fluoroalkan. We know that fluoroalkan is toxic; they are not environmental friendly, but when we did use the amine Cylon, we couldn't reach to hydrophobic surface. But I should explain here that I couldn't improve the reaction more than 6 hours here. The contact angle is the parameter that give us the information about the surface wettability. And Young has a definition of contact angle based on the interfacial energy of the whole system when the liquid has a contact with the solid. Here I bring the examples of the contact angle, and in picture A, we see MTM-CNF without modification, and the picture F shows us the MTM-CNF modification, but without catalyst. Also here I tried to show the durability and the stability of the surface when the water have a contact with the surface. I measured until 5 minutes, and all data that I reported is with 5 minutes. I wanted to see the transparency and also the flexibility if it changed, but it looks that after modification, we don't have big change in the flexibility to compare with the before modification and in transparency. We measured the mechanical property of the MTM-CNF before modification and also after modification. We see that here we increase the Young modulus when we have MTM in nanocomposite from 70 to 24. But the aim of this work was to preparing hydrophobic material without disturbing or destroying the mechanical property and the structure. Okay, then the data after modification, this modulus show that we didn't change the mechanical property, and the structure of MTM-CNF brick and mortar structure are preserved during the modification. We analyzed this surface using the elemental mapping, and here we have a carbon that it comes from the CNF and the silicon from the MTM, and we can see the even distribution here. And this picture C is about the modified MTM-CNF with the fluoroalkan. We can see here the high density of this chemicals on the surface, but and also this is the modified with the mercapto. But if we compare this picture with the fluorocarbon, we see that we have some penetration, but actually it is reasonable due to the size of the mercaptocylon to compare with the fluoroalkancylon. AFM analyzing of this surface show that we have an even and homogeneous distribution in both surface, and also here the AFM this picture is related to the modified with the mercaptocylon that we had a 146 contact angle, and we have a high roughness that it's in accordance with with the Wenzel and Casher-Baxter theory. Also here, the cross-section show us that we could preserve micro and nano structure of the MTM-CNF after modification. Conclusion of this paper is that we could prepare the transparent and the hydrophobic MTM-CNF nanocomposite. The nano and the micro structure of nanocomposite is preserved after modification, and a modified MTM-CNF with the Mercapto group has can compete with the fluoroalkyl modified nanocomposite with respect to the hydrophobicity, and E modulus of MTM-CNF preserved after modification. Paper 2 is about the designing the superhydrophobic surface of CNC with a combination of self-assembly and organocatalysis. Superhydrophobic surface have become a popular and topic of the research recently, and it's interesting, especially for industrial sector, due to the self-cleaning, anti-fouling, water resistancy. And we have several examples of superhydrophobic material in nature. One of these examples is lotus leaves. In lotus leaves, we have the self-cleaning property that it's known as a lotus effect. This phenomenon is explained with the combination of surface chemistry and also surface morphology, or in a better word, roughness. When we have a papilla at the surface of these leaves, lotus leaves, in a micro scale, that this micro scale was covered with a wax in a nano scale. Then Wenzel and Casher-Baxter, they wanted to correct the Young equation based on roughness. And this Casher-Baxter equation is more related to this lotus effect and lotus phenomena. Then combination of the chemistry and designing graph surface is interesting. And actually, scientists and researchers, they tried to do this combination to prepare superhydrophobic nanocellulose. For the decreasing of surface energy, they use fluorocarbon, silicon-containing polymers, and or fatty acid. But we know that fluorocarbons are toxic and not environmental friendly. And for the designing of rough surface, there is a group that they applied nanocellulose, and they did a microstructure of the nanocellulose, and they make it hydrophobic. And they, with a spin coating as a spray coating, they used it in a variety of surface. And also there is some study that using hollow seed nanotube in a filtration system combined with a CNF, all chemical vapor deposition. They are the method that have been used. We choose CNC. Drake Gray, who won Marcus Wallenberg Prize for studying CNC, they explained that self-assembly of CNC to chiral pneumatic phase in a suspension gives a special texture for the surface. They explained this texture also according to the evaporation method, or also with the thickness of film. When we have a more thick film, around 40 micrometer, then we will have some polygonal texture that it's related to this accumulation of this chiral pneumatic phase in a suspension form. We choose the filtration system to prepare CNC film. For this, I transferred the well-homogenized and well-dispersed CNC suspension that it was 0.05 weight% I prepared in the water. Then I transferred to the filtration system. I wait 10 minutes until the draining of water is stopped. It means that the first layer of gel formed. Then I connected to the vacuum. After 16 hours, I got the wet cake of CNC film. After drying in a rapid cotton sheet former, I could get transparent CNC film. Characterization of this prepared CNC film with the AFM show that I have a roughness at the surface more than 1.2 micrometer. Polarized microscopy of this surface show that we can see here the chiral pneumatic phase, but the thickness of the film is 40 micrometer, 40 to 45 micrometer I use. Then I try to see better, to have a magnified and to see what I have exactly at the surface. Then I magnified the same surface 40 times, and here we can see the newborn tactoid. Here they are everywhere, and also the growth tactoid and the fusion of tactoids. It means that with the filtration system and the self-assembly feature of the rod-like CNC, during the concentration, I could prepare surface with a roughness more than 1.2 micrometer. Then I did the modification of this CNC film in the presence of catalytic amount of tartaric acid. With this roughness, I could reach to superhydrophobic CNC film. But the other part of the film, that it's the first layer of gel during the forming, and it's in nanometer scale, the roughness, I could reach just to hydrophobic surface. Also, with the citric acid, acetic acid, I tried all this reaction, and even we can see that with the allele or with the mercapto, especially in presence of citric acid, I can reach more superhydrophobic surface, and the contact angle value even is higher than 160. I did the same reaction, but with a variety of alkoxysilane. But this phenylsilane show us that not only just the roughness of the surface is important, also the chemistry of surface is important, because with this chemical, I couldn't reach to superhydrophobic surface even in a high roughness. I don't want to spend here its time. They are the contact angle. I wanted to see the water resistancy of this modified CNC film. Then I soaked both CNC and unmodified and modified into the water. After 2 hours, the unmodified one was totally disintegrated. Then there was no change in the modified one. I kept it for additional 2 weeks, and after that, this is the result. It means that with the modification, I could get to high water resistance CNC film, actually. The SEM and AFM image show that in both smooth and both rough surface, we have a evenly and homogeneous distribution of the chemical. But what is the difference, what makes difference is the roughness of the starter material. I record here a video, hope it works. Yes. This is the one that I prepared CNC in the lab. And it means that, yeah, with the filtration system, this self-assembly and having roughness following with the alkoxysilane modification in presence of organocatalyst, I could prepare actually the CNC films that it showed the property like a lotus leaf. Food packaging is required to preserve food from oxygen and humidity. And currently, fossil-based material are used for food packaging due to the high oxygen barrier property. And we know that the biomaterial doesn't have the equal barrier property as like a fossil-based material. But also we know that the nanocellulose has a highly ordered and dense crystalline part that it will help us to have a barrier property. Then we thought that if we check the barrier property after modification, it would be a valuable result, because we know that it's highly moisture sensitive, and in the high relative humidity, it can reduce the oxygen barrier property, and it doesn't have a good barrier property for the water vapor. Then we measured the OTR, and here the results show that in a 50% relative humidity, we could improve the barrier property, oxygen barrier property, when we modified with the C18. And even with this material, modified material in a 90% relative humidity, we have again good OTR and improved OTR value. The conclusion of this paper is that the self-assembly of rod-like CNC through filtration system resulted in a rough surface. And the fluorine-free method was developed to prepare superhydrophobic CNC film. The film with the excellent water-resistant property was prepared. And the oxygen barrier property also was improved by CNC that was modified with the octadecyl trimethoxysilan. Also, allele and TIA modified superhydrophobic CNC film allows for further functionalizing if it's desired. Paper 3, I will talk about the direct esterification of CNC with a thioglycolic acid. Introducing thiol group onto nanocellulose will help to be useful in a metal removal catalyst support. We can use them in a solid reducing agent for chemical reaction, cross-linking agent. As we know that the sulfur has a good cross-linking property in a composite. And also we can use them as an intermediate for further functionalizing. Here is the groups that they worked with the direct esterification of thioglycolic acid on filter paper or on CNC, but they used acid, paratolan sulfonic acid and sulfuric acid, but the one with sulfuric acid for 3 days. The reaction was for 3 days. Then there is a possibility for hydrolyzing CNC or nanocellulose with this acid. Then we wanted to try with our mild condition to see how it will work. Also, preparing the modified suspension CNC is beneficial for the coating application if we want to use it. Then we did modification on either suspension form or solid form like a foam and film. For foam or film, I used toluene as a solvent in the presence of tartaric acid and I reflux it. But for the CNC suspension, toluene didn't work since it's aggregated. And also we tried with the tertiary alcohol as a solvent, but it didn't work either. Then we used acetonitril since it's miscible with the water and we could get the modified CNC. Here is the result, and the results show that when we used this modification in the presence of tartaric acid, but in toluene, we could increase the DS from 0.08 to 0.22 to compare without tartaric acid. But when we used this esterification in acetonitril, actually I tried both 3 of acid, organic acid, tartaric acid, citric acid, acetic acid, and 1 without catalyst. It shows that without catalyst in this solvent, we have a better DS. It means that we have actually autocatalytic effect of this thioglycolic acid in this reaction, but it works better in acetonitril. The DS was measured according to the method, back titration method. The characterization of this modified material with the IR, here show the ester peak around 1,710 to 1,730. But also the intensity of this IR peak, ester peak in the FTIR is in accordance with the DS that we got from back titration. Here is the solid state NMR of the modified sample and unmodified, and the carbonyl group and the methylene group show that we had a successful modification on the CNC. Here is the TEM image of CNC and the TEM image of the modified CNC. And here, actually, we see that there is no big change. This is the modification in a suspension form, but here we have some knot and interjection that it show that it could be because of the cross-linking of the SH and during the modification. Also, we tried to use this modified material. The CNC foam SH was used for the copper catalyzed alkylate cycloaddition as a reducing agent. This reaction actually without copper give both enantiomer 1,4 isomer and 1,5 isomer, but in the presence of copper 1, only 1,4 isomer 4. Then it's better to use CNC foam SH as a heterogeneous reducing agent that we can use this one several times in the same reaction. And we did this study, and actually we used it until 10 cycle. After 3 cycle, actually the rate of reaction is low, but we could use it until 10 cycle. And also we used this modified material, CNC, for fluorescent labeling. Fluorescent labeling is important and has a variety of application. We used allyl tambra and quinidine for fluorescent labeling. And also here the confocal laser scanning microscopy. This is with the quinidine, CNC with the quinidine, and tambra with CNC. And this picture is the UV active quinidine. UV active quinidine CNC, the CNC that it's labeled with the quinidine. Organocatalysts exhibited different activity in different reaction media. The thioglycolic acid exhibited an autocatalytic effect, and the CNC foam SH was used as a reducing agent for reduction of the copper 2 to copper 1 in alkylate cycloaddition. CNC SH could be reused multiple times, and it happened. And also we did a fluorescent labeling of the CNC with the tambra and quinidine. The demand for manufactured fiber-based packaging material has increased. Developing a method to improve the ester property of fiber is essential to maximize the efficiency of this product. Adding chemicals is one of the techniques that has been used and has been studied for improving the ester property of the fiber. And in this context, cationic starch have been studied and gets high interest from the paper making industry. We know that the distribution of charge on the fiber and also density of charge on the fiber will influence the absorbing the cationic starch. This is the why polyelectrolyte techniques or layer by layer techniques became popular and interesting topics to be used in this kind of project to improve the strength property of fiber. And for this polyelectrolyte, CMC or carboxymethylated CNF with a cationic starch are used in a layer by layer technique. And actually the interaction, we have an electrostatic interaction here that it's in this kind of the modification. But we have the knowledge in the group that some biosaccharide like a pectin the carboxylic acid, they can improve the mechanical strength property of fiber in the presence of organocatalyst with a cross-linking. Then we planned to design a feasible method that it can be used in an industrial and in a big scale for improving the strength property of fiber. Then we choose the CMC in this study as a polyanion and the starch as a polycation, also citric acid as an organic acid. I mixed all of them, I just homogenized them and add to the CTMP after disintegration. After just 10-minute mixing everything together, I made a sheet with a rapid cotton sheet former. Z strand of CTMP and burst strand of CTMP show that when I used tartaric acid or citric acid, I have a better result and citric acid is even better. Then I continue my study with the citric acid. For this, we choose the CTMP pulp. And here in entry 2 and entry 3 and 5, we can see that adding catalytic amount of the tartaric acid or citric acid improved the Z strand and the tensile strength to compare without adding catalyst. But in other words, instead of cationic starch, we choose the chitosan. Also, we see that chitosan and CMC improved the property, but the effect of catalyst actually here is not clear. Also, I did the same experiment with the bleached sulfite pulp, and we see that in the presence of citric acid, actually, I could increase the Z strength and tensile strength of this pulp, but the same result as CTMP when I had chitosan. We don't see the clear effect of the catalyst here. Burst strength of any material is one of the important property that show the resistance of this material against the rupture. And the paper as a primary constitute in the packaging material, it's better to have this good property. Then with this method, we could increase the burst strength of CTMP around 78%, and for bleached sulfite pulp, around 52%. Here is the same image of the CTMP and BSP before treatment and after treatment with the cationic starch CMC and in presence of organic acid. Actually, the same image show that we have a high dense fiber, and after treatment, we could have a better fiber joint. We want to study the distribution of this polyelectrolyte. Then what we did fluorescent labeling of cationic starch. Okay, then I did the esterification with the thiocholocolic acid, then followed with the allyl tambra or quinidine to prepare the fluorescent cationic starch. Here also, this is the image that it's with the allyl tambra. Then I applied this cationic starch as same as the previous method that I did for the just normal cationic starch. And after preparing sheet, I checked the confocal laser scanning microscopy. In case of bleached sulfite pulp, we have the heterogeneous distribution of this cationic starch. But in case of CTMP, we have an even and homogeneous distribution of this cationic starch or polyelectrolyte on CTMP. that it follows the lignin pattern. Here is the autofluorescence emission of lignin. But the starch that I labeled with the kinidine, I couldn't use on fluorescent labeling of CTMP because the kinidine has the same range of emission with the lignin, but I could use it for labeling the bleached sulfite pulp. And also it shows that, yes, we have a heterogeneous distribution. It seems that the presence of lignin helped to have a more polyelectrolyte on the surface, and also we have a better effect actually in CTMP to compare with the BSP with this method. The tensile strength, Z strength, and burst strength of CTMP increased. Respectively, we have a 57% for tensile, 100% for Z strength, and 78% for burst strength of CTMP. But for tensile strength of BSP, we have a 54%, 31% for the Z strength, and I could increase 52% the burst strength of the BSP. And we observed the near doubling effect on strength property with a cationic starch and CMC in the presence of citric acid to compare when we didn't have citric acid. And polyelectrolyte complex follow the lignin pattern of CTMP pulp and is evenly and heterogeneously distributed in a BSP that we don't have a lignin there. And it was studied with a confocal laser scanning. From this thesis, we got some lesson and we planned some future work. Designing a water-based catalytic surface modification is our future work. Part of this study will focus on designing a rough surface, either before or during modification. Actually, patent has been filed for this work. With respect to direct esterification of CNC with thiocalcic acid, we need an alternative solvent. We don't want to have acetonitrile in the reaction. Studying the oxygen water vapor barrier property and water vapor barrier property of hydrophobic MTM-CNF and MTM-CNC nanocomposite will be interesting, since we know that adding MTM improves the barrier property. Preparing new nanocomposite with a thiomodified CNF or thiomodified CNC in a suspension form and with a clay, it will give us the opportunity to have a high mechanical property of this nanocomposite. And using fiber treatment with a combination of polyelectrolyte and organocatalyst for modification for the other kind of the CTMP, or combining them and comparing this method with a different refining parameter will be valuable result. And using the different ratio of cationic starch and the CMC within this method, it will be in our future work to see how we can improve the mechanical property. And it will be even more interesting if we combine this method with a hot pressing. I am here now to acknowledge all people around me that they helped me during this, my PhD time. First, my supervisor, Professor Armando Cordova. Thank you for your time. Thank you for your nice scientific discussion and introducing me to this interesting field. Professor Bylund, thanks for your kind and help, and you helped me to be in this university and to get this position. Thank you. I would like to thank all members of the E2CMP project, Tiny Bee Talented project from the Mid-Sweden University, Villerid Korsnäs, Valmet, Tetra Pak, More Research, Pulp IB. Especially thanks to Professor Per Engström for nice and helpful guidelines. I would thank Professor Lars Berglund and his group for nice collaboration during this time. We had nice collaboration. Many thanks to Professor Beckwell from Stockholm University to reviewing this thesis. Thank you to Professor Monica Eck and all committee for your time and accepting to evaluate this thesis and my dissertation. I was lucky enough to meet a lot of nice people in Mid-Sweden University, nice colleagues, everyone at NAT, Share, Electronic Design, especially Håkan Norberg and Turboy for being kind and all the time and helpful. Many thanks to Inger being here. Thank you for nice organization. And I would thanks my colleague in the organic chemistry lab for your help, being friendly and nice time. Administration office, library, janitor office, printing office, IT department. Thank you. Thank you for all help. I would thanks all my friends for all kind of support and help. And finally, thanks to my family for all kind and support. Thank you. And thanks to all audience and thanks for your attention. This thesis is dedicated to my parents.